This might take you.
Yeah, sure.
Sydney Coleman is going to release. So his students are going to work on David Physics over quantum mechanics. He was a student.
So, David Griffiths was Sidney Coleman.
Grad student.
Sidney Coleman is dead.
He's dead. He's not dead.
Okay.
Dr. Harper?
Yeah.
So in your earlier days, have you ever interacted with Sidney Coleman? Have you
Say that again.
No, have you ever interacted with Sidney Coleman, like the famous
Oh, a
quantum
long
field
time
theorist?
ago. Yeah, he actually came to Irvine shortly after he discovered I don't know what it was. It was something to do with SU6.
Oh, okay.
Yeah. I believe he's in Canada. Is that right?
No, he was at Harvard.
At Harvard?
Yeah, I think he
Yeah, I
passed
may be
away in
confusing it with-
2003 or 7. I don't. He passed away a long
Yeah.
time ago.
Yeah, it's that's quite a long time ago, so I don't remember details. Anyway, today we've got the tensors in ranked 1, 2, and 3, and we're going to be using the permutation symmetry. But the most important part of this is the understanding of the intertwining between these two kinds of symmetry. And it's not that different from the intertwining that exists between the inside and the outside in this Mach principle that we started using right away when we did our first non-abelian group. That was D3. Well, D3 and S3 are isomorphic, so we're going to be using that and seeing some of the complicated stuff associated with this show up as a lot simpler from the viewpoint that we had before. So I would keep these two computers more or less in sync so that we can make comparisons. But the basic idea is that we have here, we're imagining a U2 transformation. Now this will just be like the spin a half irreducible representation in the spin up and spin down basis. That goes without saying, and I see a typo right there. That should be a 2. What we mean by 1 and 2 today, when it's in the subscript of the D matrix, is for most of the physics that we're talking about, spin up and spin down for spin a half system. Now, this would be more old-fashioned notation in which you're kind of making a state as a psi or a phi, and the matrix elements with little parentheses. But most of the time we'll try to use direct notation because if you use it right, the permutation and unitary intertwining is easier to see. So in any case, either one of these is a transformation of the unitary group U2. And matrix representations are really important today because they're kind of slide rules. And I'll show you how to let the computer help you with a matrix slide rule. This is something I really just noticed this weekend after tearing my hair out trying to do some arithmetic the old-fashioned way. So when you talk about a ring 2, now 2 particles, each of them enjoying the same sort of U2 state space, then that's 2 times 2, or 4 states that we'll indicate with Dirac symbols, 1, 1, 1, 2, 2, 1, and 2, 2. Old-fashioned notation is shown briefly here. And this 2-particle transform, the way we can write it concisely, is to say that the transformation, a little prime here that happens after you've applied the unitary operator, whatever it is, then gives you linear combinations which have this double index form. And I'm very often going to use the cross symbol, which is appropriate for mathematical purposes, to indicate that I have a product of 2 transformations, 2 essentially identical transformations. that are working on our rank 2 tensor space. Tensor in the sense that it's a product space. This is nonlinear group theory again. Now what we're putting together here isn't that different from what we had to put together for the 21 centimeter problem involving the spin of the electron and the spin of the proton in atomic hydrogen. And we went through that pretty quickly. Now we're going through it again just to get us a feeling for the intertwining group theory that we're trying to develop here. In any case, as I said, matrix representations are important, and this 4x4 representation, we showed that briefly when we did the hyperfine hydrogen problem. And it's, don't forget that when you do these outer products, you see a 2x2 matrix times the first component, and the same 2x2 times the other 4 components in respective positions to make this. So it's the notation, the tensor notation, that can be a sort of bothersome and problematic for what we need to accomplish today, but we'll try to get that under control. Now, what's going on here, of course, is that while we have the unitary group working on this huge space, we also have a group that's going to help us. And that group is just the 2-particle permutation. In this case, there's only one active operator, and that's the transposition of particle A with particle B. And the basic idea being that when I apply this operator, I mean to either interchange the A's and the B's, or change the states that go with each of these guys. In this case, I'm doing that. But about halfway through this lecture, I want to really clarify that. That's something I worked very hard on this weekend, to figure out what's the best way forward to get rid of some of the problems that this stuff has for computational and for pedagogical purposes. So we'll get to that in a minute. But right now, the A and the B refer to labels of perhaps identical particles. It would be nice if they were, because then everything works. And so we will be dealing with shell models, and we also will be dealing with the identical atoms that sit on rotating molecules that have symmetry because the atoms are identical. In any case, the transformation matrix for this is really very simple, because there are only 2 states out of the 4 that really need to be looked at for permutation. That is, this one is a permutation of that one, but each of these are permutations of themselves. So the matrix that does the transposition just has a diagonal 1 for the 1-1 state and the 2-2 state, but then 1-2 and 2-1 go into each other, and therefore you have an off-diagonal matrix, submatrix of the permutation matrix. So this is the kind of shall I say, road mapping that matrices do. This is what makes matrices powerful for understanding what was going to be a often a confusing mess. So here we have the possibility, and I want to make a really make this a certainty rather than a possibility, that the permutation operator should commute with this matrix up here. Okay, so no matter what of the infinite number, continuous infinite number of unitary operators there might be, I want this thing here to commute every single one of them. And that's the key to the intertwiningness of the permutations and the unitary in this setting, and something we're really going to emphasize in many different ways today. So I come here with a permutation operator, and all it does is switch the indices. Big deal. You wouldn't think that would be worth even a notation. And furthermore, the so-called dummy index rule could be applied here, and once I do that, I get this expression here, which then results in our unitary guy sitting on the other side. Here are the actual phi wave functions, an old-fashioned notation here, kj, and that's the permutation operator of jk, which is what we started with over here. Okay, so this is kind of a one-line proof, maybe with more pieces than it really needs, but still, it's kind of, you know, suspicious. We really want to check this. This is what I call trust but verify. So the idea that this commutes with that, we need to see that in explicit detail. This is very symbolic, but we need more than that. Okay. Yes.
The representation, you know, that phi j and that phi k down the last line.
Yes.
Uh,
That could
they are-
easily be.
you're
Yeah.
representing them as direct gets.
That would be okay.
Okay, it's because
That'd
I'm
be
trying
okay.
like to from that step to the
Yes.
next step. I'm trying like to or use
Yes,
the orthogonal
this is-
expansion of that.
This is most of the time what we use. I just wanted to keep the old-fashioned thing that you'll see in
Okay.
books
Okay.
going back to Feynman. Okay. The other thing that I should make a point of before we go on here is that this has a shorthand too, right? Basically, the shorthand would be just some big D or the D cross D. That's the whole imaginary matrix that we're making out of this. And then there's the double index that goes with that, right? This is a very common, I think it's called Kronecker notation because of the Kronecker product. This is called a Kronecker product. Kronecker was a big deal group theorist from long ago. Okay? And some of these guys we ought to look up and, you know, put pictures of them up here more often. I've been doing it some, but I forget because I've got this stuff to work with. It's got me bothered and I don't remember to make it. So, this is the idea that the S2 group, symmetry operators, only two of them, is the symmetry of the monster symmetry, U2, in the sense that it commutes, and vice versa. In other words, I can derive properties of this one using this, but I can also turn it around. Sometimes I can use this one to make sense out of this one. And that's the intertwining that we need to explore more in a few more slides ahead. Okay? So, as I said, trust but verify. So, it might help to just plain write it out and see if this question mark can be erased. In other words, if I take this matrix right here and multiply it by this one, and then take the same matrix, multiply it from the right-hand side instead of the left-hand side, do I get the same matrix? And the answer is you don't. And you'll see that. But as far as we're interested, you do. Okay, so this is kind of worth doing. Okay? So when I multiply these two together, I notice what it does is it switches to columns. That's kind of neat. Mid-column switch. Whereas if I multiply by this one, it switches the rows. These guys cross. I just take this whole row and stick it down here. So is it true? Is it true what we're saying here? Well, yes, it is, except, and that's the thing that's kind of interesting about this, the matrices are numerically equal, but the some things have happened. Okay, we've switched the factors. Instead of getting 1, 2, 1, 1, I get 1, 1, 1, 2. Right? No big deal, but it should be noted that that has happened. Okay, and this is the kind of thing that happens a lot with these tensor products. But the symmetry is verified here. This is a slightly different way of writing than that one, and they're both different from that one. So that should be noted.
Dr.
Yeah.
Can you go back one slide?
Let's go back to that one. That one.
No, one.
Oh, you mean a whole section before this. This. You see, this is the
So are there? So those
theoretical way of writing. So what I'm saying here is this operator commutes with that one. thinking of it as a matrix now. Okay, our SAB is this guy right here. Okay, this guy is this whole thing. And there's an infinite number of these. There's only one of these right now, but later on we're going to have n factorial of these. And we'll have, I mean, this is a double infinity, right? Actually, quadruple infinity. Actually, octuple, because it's real and imaginary, right? And every single one of those components. Okay? So this is a monster. This guy's just a lonely little 4x4 practically diagonal matrix of zeros and ones. All right? Does that answer?
Yeah, it's because I was doing the computation right now.
Okay.
And see, like, but I know, like, I have to, like, move some stuff.
Okay.
I just wanted to see, like, if I could prove fast enough, like, the,
Let me go ahead and leave.
like the commutation relation between the,
This page, I'll leave this page up for the time being. Okay. Now, that's all fine. But I want you to notice that this is also S2 to symmetry is going to apply not just 2-particle, but to 3-particle, which we're going to do today, and later on, 4, 5, 6. We'd better be able to do that, and finally be able to do 60. We're going to do buggy ball, right? So this kind of symmetrization, anti-symmetrization, just 2, S2, applies to high dimension. So this is fairly simple by comparison to what that will be. Okay. Now, what I'm saying here once again is if SAB commuted with this, you might assume it passes right through to give you one, leaving this thing unchanged. And I say this is true numerically, but all the components have flipped order. Okay, when you do it, when you multiply this thing by this, you get this. Multiply it on the other side, put them both together, that's what we got there. Okay, so each of these A, B, C, D has become C, D, A, B when you go through there with that matrix. Okay. All right, let's put that aside for now. What we want to do is build the projectors that will, well, diagonalize the permutation matrix. That is going to be easy. It's a little 2x2 matrix. It's easily diagonalized in the half sum and half difference. So this is a good old minimal equation of a transposition whose square is 1, or whose difference with this 1 is, whose square, the difference with the 1 is 0, factored into AB plus 1 and AB minus 1. There's another typo right there. Put a minus sign there. It's always doing this copy and paste and never changing when I paste. Okay, but here it's right. That's the symmetric guy, and that's the anti-symmetric projector. And the notation, horizontal, vertical, respectively, for symmetric and anti-symmetric. So, right from the beginning, the notation is at first looking to be totally unnecessary, but as we'll see, it becomes powerful for other reasons. In any case, the actual projector matrices now are easy to take. We're taking a unit matrix, and then that matrix that had 1, 1, 0, 0, but both of them have that. So we're adding those, taking half of what we get. And that is the idempotent operator that will project. Now here with a minus sign, I lose components right there, and I put a minus sign right there. But here, everything's positive, and we have both of the upper and lower diagonal components sitting there. And then the deal is, if you remember, we're making what we call a Dtrain T, okay, a transformation that we're going to apply to the infinite number of unitary 4x4 matrices. So the idea is that we pull off linearly independent, that is mutually orthogonal components, and normalize them if you want to go at this in a very direct matrix, shall we say, methodology. So I see this guy right here, I put him in here. Don't have to do anything to him because he's already orthonormal with just about everything. And then this one with two guys in it. Okay, well I need to use the idempotence properties, take the square root if we're going to have a transformation matrix that works. And then here's another one, it's linearly independent. But I don't put two of these in there. You can't have linearly dependent columns in a transformation matrix because it's supposed to have an inverse. And if you put those in there, it would not be, it would be singular. And then finally, after I get done, I have just one to pull off of here. This is linearly dependent on that. So just one thing gets to go in there, and it gets normalized by the same square root of 2 that this one did here. Okay. Now, the question is, where do we put this transformation matrix when we apply it? How does it go to do the diagonalization? That's what this Dtrain stands for, a diagonalizing transform of the permutation matrix that we had there, the 4x4 matrix. And the same diagonalizing transform is going to go to work on all those infinite number of U2 operators, the big 4x4s with all the D's in them. So that's the thing. We want to apply it first to the permutation matrix. That's easily done. But where does it go? Well, it doesn't go on the left. That is something you should really watch out for. If you're talking about columns, you're talking about kets. And kets have the flat side on this side to work on whatever matrix you're going to work on. Then the transpose of that is what you apply on this side. So this is just basic matrix algebra, but it can be easily forgotten and missed, right?
Or like the convention, they'll have that dagger in the first term. I've seen that written quite.
That's right. This time having the dagger on the first term is a little squirrely at first, but then you realize we're making kets here. If I want to make bras using the projectors, that's fair game, and then that would go over here. That would work, okay? But this is kind of maybe easier when we talk, because these things are going to get big fairly quickly here, so you want to probably keep the columns as your starting point, and then you just get this one on the side, okay? So the question is, what happens to this matrix, and how do we interpret it? What's really going on here, okay? So I multiply these two together, okay? Get ready now to actually produce the transform permutation matrix, okay? And there's a result. The result is we have diagonalized this thing. This is an abelian group, so it's completely reducible as a matrix to 3 symmetric eigenvalues, and then the minus for the anti-symmetric one. Okay? So we get 3 symmetric irreducible representations on the first 3 upper diagonal components. Then we get the one result, minus 1, for that representation. It's called the anti-symmetric representation.
That
This
really
guy right here.
looks like
Okay.
the matrix where you have like the space-time, like the metric tensor.
Say that again.
Like when you have like some people write it like -1, -1, and 1, and some people like you have it right now they have it 1, 1, 1, -1.
Well, if you're trying to be nice to the S2 group, and the S2 group's eigenvalues is what you're displaying, there's no question that the eigenvalue of symmetric is +1. And then this guy, no question that it's -1, okay? You may be confusing this with the metric coefficients
Oh
of
yeah, I
the
was
Rent's
just
group.
making the trying to relate that to like when they have like general relativity.
Yes, now you're talking about a metric. That's a whole different story. What
So,
we're talking
okay.
about here is a permutation operator.
So that that game that they have with the signs and they put like minuses and pluses and minuses or,
Right.
or whatever. Do that has to do like any symmetry or like
Convention.
Well, there, essentially, you would say there's a binary choice here.
no?
Do I want to have my metric be r dot r minus ct squared, or do I want to have ct squared minus r dot squared? I mean r dot, right?
That's why they choose like some authors you choose like minus plus
It's
or
convention.
plus minus.
Or, yeah, you can start off with a minus and then go plus if you wanted to. I don't see that very often. But very, very much I see the spatial part coming first and the time part second. And then if you're going to write that, then you have the minus sign inside the expression for the metric. It isn't sticking out on the left, right?
Okay.
It's purely a matter of printing custom there. Yeah, it's
I was just trying to find the relation or the connection with
There.
syntax.
We're just-
in this particular case, I agree, you have a matrix 1, 1, 1, 1, minus 1 here. But at this point, it has nothing to do with the relativity. It's just, this is complicated enough. We don't need to bring in space-time yet, maybe later, but not quite yet. Okay, now, what's going to happen when we take this monster and multiply it? Okay, that's a little harder than this. We've got a little bit of algebra to do here. Okay, so that's what I want to show. So we're going to be comparing what happens to the permutation side of this intertwining marriage that we're getting involved in here, and what happens to the unitary side. What happens when T dagger unitary T, and this is a very complicated, much more complicated thing. Well, takes a little while to do all these multiplications, but here's the first guy right here. These two have gone together to make that. It kind of looks a little bit messy, but we haven't done this one yet. When you do that one, we have just derived an expression for the irreducible representation of a momentum 1, 3 states. That's kind of neat. This is a symmetrized outer product, and we didn't really make a fuss about this when we were doing the hyperfine problem with proton-electron spins. And then that down here, you see we get zeros here and zeros here, so this one has definitely reduced. And it's to be compared with this one, which completely reduced. But this one just reduces as far as I can possibly get this thing to go for all of the infinite number of elements of the unitary group. Now, this is not just for the unitary group. We've been saying that because I made this a unitary matrix, but this is a GL parentheses 2, general linear two-dimensional transformation will undergo this, and this will be an irreducible representation of that. So if you want to do relativity by 2 dimensions, this is it, you're fair game. You can do this. Okay? That's kind of neat. All right? So this is how the permutations are going to police the monster, the unitary. This is an intertwining algebra here. This commutes with that. Clearly, this is a unit matrix, right? And it commutes with everything. And then, of course, numbers commute with numbers. So this whole matrix here has to commute with that. We're seeing the result of that S2 symmetry by looking at this is the easiest problem that we solve with.
What would be different in that block diagonal matrix if the dagger was in the right D? Like if you have like D, D.
This thing? Oh, go ahead and try it. You get a mess.
So if you have like D, D,
Yeah.
Kronecker, D, D dagger.
Yeah, you definitely, I mean, just go back and do this backwards. It ain't gonna work. put this guy over here and that guy there, it ain't gonna work. So be cautious, because you waste a lot of time if you try to
Because
put
that's how
this thing here.
they usually do, like T matrix, T dagger.
Right. Not here.
Huh.
You do that, you're screwed.
Okay.
Yeah.
Is there
You can see why it is, right?
yeah, I mean, yeah.
Because we're pulling columns off of the thing. They're kets. The kets have to flatten up against the thing here, right? Now, if you want to make bras, they're flats on this side, right? Because they're rows, right?
So it
Getting
makes
ready to
sense
multiply
do-
here, right? These are columns getting ready to multiply these rows. It's just the way matrices are put together, right? So if you change that around, you're screwed. It ain't gonna work. Okay? So I probably saved you maybe a day of sweating your hair and pulling your hair out. You got plenty of hair to lose, but I don't. So, I really do want to emphasize that we now have a near disk representation with J equal 1, which we looked at before. Big surprise for us, right? Because we've already done the hyperfine problem, and that's exactly what happened. But now we're looking at the guts of it. We're looking to see how the gears work inside that analysis. And normally we would have gotten this by Clebsch-Gordon coefficients, right? We haven't used Clebsch-Gordon here. Okay? So we're deriving Clebsch-Gordon coefficients by symmetry. Very important. That's what this is. This is a table of Clebsch-Gordon coefficients. Okay? So, see if there's anything else I need to say. A symmetric and one antisymmetric. And again, I've already said this, but clearly this commutes with this. And that's what's going to happen. Every one of our intertwining things is going to commute. And we've seen this intertwining before when we went to the Mach-Mach principle for D3. That's coming up here, but in a completely different form. Now, here's another thing I had to do in order to make all this work. I had picked a particular geometry for this and gotten a particular group table, which for the kind of things that I have written down on permutations is not compatible. Now, do you see the difference? If I cover up this thing, which tells you the difference.
Yeah.
The convention.
I just flipped sigma 1 with sigma 2. Okay? Completely different group table. Okay? Than this one. This is the one that came out of this. We have it in AMOP class. You can go back and look at that, or class 14. Or you can go back to group theory lectures. I've been using this for a long time. I'm switching. Literally. I'm switching. Okay? So, let's now do what we really need to do here and get the Mach-Mach principle down in a way that is manageable for permutation geometry. So, I'm going to, as I say, match these two computers here, and this is a good place to start. Particularly since from where I stand, it's hard for me to read the title. But that one is showing it clearly. So, this is the connection between the unit, very obviously unicycles, and then, let's jump down to here to the reflections. Each one of those reflections is a bicycle. Easy to remember if you think of A, B, C being 1, 2, and third order in the alphabet. The 1 goes here with a 2, 3. The 2 here goes with a 1, 3, and the 3 goes with a 1, 2. So it's in a good form here to not cause you trouble and have you remember what these things are. The one that's weird is that the 120-degree rotation, 120 in the clockwise direction, which is what we need to do with this one, that's this operation right here, is going to be married to the cycle ABC, or 1, 2, 3. The inverse of that is 1, 3, 2. And remember, you can write these cycles 3 different ways. And we'll be doing all of that to make clear here what the symmetry. But we've already been through a lot of that already, and I want to make use of it now. Okay. So we're going to be able to, and the thing that's really, I think, good about this is that it lets us do the Mach-Mach principle really clearly. What we're going to have, you see, is a body of this, whatever it is, molecule, like could be electrons in some sort of a solid that had trigonal symmetry. And then we're going to have a laboratory, which are the pockets, so to speak, in which the particles A, B, and C fall in various permutations. So that's the deal, is that we have lab or state-based operators indicated by black here, and permutation symbols that have bracket, I should say braces, I guess is what you call the lines. I don't know if there is. The brackets, I think, are the ones that have the little squiggle on them. Braces are more like that, I think. But anyway, that notation, just to distinguish it if you're colorblind from these, which will often color in red. So that's sort of the inside of our system. It's got blood, right? It's got its red there. Okay, and this is the outside. If you're well tanned or African American, you're black on the outside. Okay? So that's what we're going to deal with. And every one of these things is going to commute with every one of those things. So all of the things that happen with Mach-Mach are going to be here in very clear terms, much more clear than it was when we did that with D3 all by itself. Okay. So here are some interesting states to look at and operators to go with them. The original state is going to have the A particle in the 1 state, and the B particle in the 2 state, and the C particle in the 3 state. So think of that as the particle actually in a bucket that's labeled with 3, B in the 2 bucket, and A in the 1 bucket. So that's our original state. And then we're going to have linear combinations of 3 factorial states that we're going to be working with today and in the next lecture. And in this case, the states definitely have to be more than just spin up and spin down. So this is definitely something that's going to have the group U3 behind the scenes. Now, it can be the group U3 that goes with the states. That's the most common situation, a 1, 2, and 3. But it also could be the U3 that goes with the internal particles. If they're nucleons, they're liable to change into other particles. There's all kinds of things that can happen. But usually we don't do the unitary transformations of the particles. They're sort of inviolable for most of the work that we do. Certainly if it's an electron, it's not going to change. It's a thing that we can think of as being immutable. Now, the first thing that's looked at here is what we have is a lab-fixed particle 3-cycle effect. In other words, what happens if I do the lab-fixed thing? That means I'm going to imagine that the A, B, and C is applied to the particle. The particles are actually going to move. A goes to B, B goes to C, and C goes to A is what this says. Okay? So A goes where the B is. Okay? That's actually right there. Okay? After this transformation. And then, according to A, B, C, after you've done that, then B goes to where the C was. So there's B now sitting where the C was, and so forth. Okay? Finally, C winds up where the A was. So there's a nice tricycle transformation which takes the state, the original state, 1 in A, 2 in B, and 3 in C, and turns it into the state 1 in A, 2 in B, and 3 in C becomes 1 in C, 2 in A, 3 in B. That's, or B in 3 is another way to say that. I should probably say that as state 1 over C, 2 over A, and 3 over D, as if the state would grab a particle from up top, okay? And it is perfectly right, and I'm going to emphasize this several times here, to rewrite this. All we care about is the relative position of the states 1, 2, and 3, and those particles A, B, and C. Now here's the corresponding transformation here, 120-degree rotation, okay? But this is particle phase. This is the lab rotation. Now, that's what makes this thing powerful, is I can look at it in a number of different ways. And so here I'm going to do something that takes state 1 into state 2, and takes state 2 wherever state 3 was, and then state 3 is going to get shuffled back to where state 1 was. So literally, that's what happens here. 3 goes back to 1, 1 goes over to 2, where 2 was, and then 2 goes over where 3 was. So it's the same sort of nomenclature, same sort of placement of things that we've been using pretty much here. Now what's interesting about this R, and I put a little bar on top of the ones that are particle fixed. It's a little bit of a deviation from the notation that we were using before, but bear with me. The thing that we notice is, and we notice this in a number of ways of looking at this, but in particular, we're going to get the same arrangement if we do the inverse of R, that's R squared. Here, if we do, instead of 1, 2, 3, we do what is effectively, if you number the A, B, and C, is 1, 3, 2. That's A, C, B. But that means we're going to move these things accordingly. A is going to go where C was. That's over here. Okay, so there it is. C is going to go where B is. So C is going to roll back to here where B was, and then B has to get out of the way and go. The only empty space left now is here. So there's a 3-cycle. Let's see. You would say the inverse of this. And that is the way it has to be, I think, to be the most efficient, this whole business. Okay? Now the result of that is that the group table for the things, and this would be normally written in red, if we're going to anthropomorphize the inside of this system where the particles reside, if we're going to do this, it is really nice if the group table for this is virtually identical to the group for it, not inverse, but same. So BC is going to be 2, 3. AC is going to be 1, 3. AB is going to be 1, 2. Aside from that, the tables are the same, and they're the same as this. Okay? So this is why I switched. I had to get this. All 3 of these group tables are identical, and we work them out in the same way. Such and such goes to such and such goes to such and such, reading to the right in all of our lists of either states or particles. And when you put the subscripts on that, that's telling you where each, or what state each particle's in, or where the particles are relative to the system of states. So I thought that, you know, this is what we have to do in order to make this not such a pain in the ass. And that's what permutations are. They are definitely, if you don't do them right, a serious pain. And not just your ass, your head too. Okay, so we're trying to avoid that. All right? Now here is a typical example of some of the operations, just to clarify it. What I'm doing is applying to this particular rotation another rotation. Okay? Now this time it's not so hard because the thing that I'm going to ask you to do is an I3 or a sigma 3. And that's the thing, I'm mixing the notations here. I didn't want to use that. So here's a group table just pulled off of the literature that goes with this chapter 25, I believe. This again is the same as this group table. It's just that I's are sigmas here. You can see there's I2, I3, there's sigma 2, sigma 3 right there. So all 4 of these group tables are identical in physical operations. Okay? But in any case, the idea was I wanted to do another operation just to get a product. Okay? So the effect of doing another operation AB on something that has already had an ABC done to it. In other words, do the product of AB and ABC. Now remember how you figure that out without looking at the table. A goes to B, and then B, and you're reading to the right. So the first thing in X, you read second. Anyway, A goes to B and B goes to C. So I know this is going to be A, C, but where does C go? Well, C goes to A, so this is a closed bicycle. And that particular bicycle, AC, that'd be 1, 3, goes with I2 or sigma 2. Depending on whether you want to do C3V or D3. Okay? So let's advance this slide over here up to where we are here, which is about there. Okay? Just to make sure it is clear. Okay? I do the same thing over here. I say, hey, let's apply to this thing. It's already had this transformation done. Let's apply a body, a state permutation. Say 1, 2. Okay? It's not too different from AB. In fact, since they're bicycles, we don't have to worry quite as much as we do with tricycles or higher. But that thing applied here, 1, 2 to 1, 3, 2. 1 goes to 2. Okay? And then 2 goes to 1. So I know 1 is not going to move. Okay? Then I go and ask, well, okay, what about 2? 2 goes to 1, and 1 goes to 3. Remember, I'm reading to the right, even though the operation is going to the left. That means I have a 2, 3. Okay? And you check it if you want to, because this is going to say 3 goes to 2, and that's what this is implies. So, 2, 3, that's I1. Okay? The effect of these two together is I1. More examples here. And these are all things that I claim, if you study them carefully, you've pretty well covered everything that we want to say here. So here I'm just showing it from the beginning. AC applied to this guy right here is equal to that. 2, 3 applied to this guy here is equal to that, and so forth. Each of them examples of operations, but let's just take one of them to ridiculous extremes. After I get done with this, there's 6, that's 3 factorial permutations that I can write that all equal. Only relative position bounce accounts here. And that was the Mach principle, right? Only relative, that's all we cared about. Outside, not caring. It's totally vacuum symmetry, and it's only the interaction between particle and states up here, or the molecule and its laboratory, if you will. Okay? So in each of these, the particle 1 is sitting, I should say the particle A is sitting in state 1. Particle 3, I'm sorry, particle B, I get confused, and that's why it's so important to separate things here. The particle B is sitting in state 3, and C is infested by state 2. That's another way to say it, right? And that's true for all of these. Okay? So there's a lot of redundancy. Now, of course, we can come in and say, hey, I just put your whole machine inside something that doesn't have any symmetry. That means that there's a lot of operators now that are going to mix these guys. and now they're going to be important, right? Now you're going to have a bigger inside. So you just move back, your outside now is going to have operators commute with every one of these. Now does your head hurt to think about that? It should. That's what quantum mechanics is all about. You've got this little region of stuff that you're really tracking the phase of, and then there's a boundary, and everything outside of that boundary, you are not tracking the phase. It's classical outside, and noisy and terrible, and it's trying to ruin your inside. Okay, if you're the ones that likes to keep the phase. Can't keep the phase, baby. Outside's going to get you eventually. Okay, so let's go on here, and I think we've got plenty of time to do this with S3. Okay, this is a big jump. Right? 1, 2. Jumping to 3, big deal. Because now you're dealing with non-commuting permutations. Unitary 2 doesn't commute. But you can always find subgroup does. This one, S3, very non-commutative. Most of the products in there don't commute. So we're going to have a rank 3 tensor basis now. 3 particles each with U2 state space. Okay? And we're going to start off, here's the identity permutation. And of all of these 8 states, and you see we've got 2 to the 3rd power, 8 states of spin up and spin down in various combinations, starting with up, 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 that's 1, 1, 1, and ending with down, down, down. That's the economy if things keep up the way they are. Okay. All right. Unit here, but a bicycle, 1, 2, what does it do? All right. It does nothing to this, and now we're counting as states, okay? So the A, B, and C are underneath there, but I'm not writing them. I'm just going to assume that 1, 2 does what 1, 2 is supposed to do, and that's take 1 where the 2 was and 2 where the 1 was. So this thing should turn into 2, 1, 1. Okay? Now, if it's just 1, 2, it shouldn't change, and it doesn't. So this is the same as that. Okay? It's this guy right here that does some funny stuff. Okay? This one turns into 2, 1, 1, which is that one, right? And this guy here does similar thing. Okay? I put 2, and it becomes 2, 1, 2. Right? And so on, down the line here. Okay? This guy becomes 1, 2, 1. That's that one. You jump back, you get to that one. Okay? And then this one, same thing. 1, 2, 2. It's back here. Alright, so he's on the upper side of the diagonal. Then all the rest of it is right on the diagonal. So there's your permutation 1, 2. 2 down, counting this one, 4 to go. This is 6th order group, right? 1, 3, okay? Bicycle. Now this could be AC or 1, 3. That's true, the bicycles, okay? Now be careful with the tricycles. But there is the same deal, okay? As I do the 1, 3, okay, that's these 2 guys, well, nothing happens to that. But this one does happen, you see. Changes to 2, 1, 1. And this one, 1, 3, it's on a diagonal, okay? It doesn't change. But that one does. And that one does. And everyone until we get to that one has got a problem with 1, 3. It gets thrown off to the side. All right? Okay. Now, here is all of the bicycles sort of lined up to look at. And here is a tricycle. Now that's when you have to be a little bit careful. But this guy, inverse of that guy, there's the inverse matrix. Now I have to roll through the thing. All three of them move now. This guy right here, 1, 2, 1, rolls into 1, 1, 2. 2, 1, 1 rolls into 1, 2, 1, and so forth. So every one of them gets moved except this one and this one, which have completely the same state in all three particles. All right? But you will notice that this is a transpose of that. So that's when you're going through making these things, you want to check that, because most of your permutations won't be mutually inverse. Okay, that's all 6 of them right there. And what's really clear from this, so if I'm going to work with this, I need smaller boxes. Okay, I'm just going to be writing 1s down, maybe -1s at later on, or, you know, I actually will be having some square roots and things, so I don't want to make them too small, but I definitely need to look at smaller real estate. This is going to happen to all of us as the world becomes more populated. You're going to have to look for smaller house, if you're moral, right? I mean, we're in, you know, exponential world. It's growing exponentially. Well, so before we do this, before we actually project this thing and do all of this group theory, I do want to make sure that you've seen this. We've already talked about it once, but I want to make it clear there is this magic formula of Yamanouchi that lets you derive the transpositions, which make up all of the group operators. Every operator, how many cycles or how big the cycles are, doesn't matter. You will be making it out of these things. These are the basic elements of the permutation. So having a formula like this involves the length of a hook for a particular diagonal element. And then the question is, what in the tableau number is sitting there at that box and what is sitting at that box? Well, then that box will be appearing in the cycle that you're talking about, this particular bicycle. And the distance between them is important. It's kind of like there's a Coulomb force between them. And as we go out, the off-diagonal things behave more or less the same. The numbers remain more or less the same. But the 1 over d, as you get to very big distances, the diagonal part gets small. That's kind of neat. Okay, the diagonal part gets small. So as you make, you know, connection with this, the diagonal part is not the issue. It's all in the diagonal elements. Anyway, the square root of 3 over 2 of 28.7. It's a lot bigger than 1/2 already. And this is only the simplest non-symmetric tableau that we're looking at there. Anyway, here's a good example from S5. That's the group that we'll need for the icosahedral group. It is essentially a subgroup of this, a halfway subgroup, the even operations of this group. And this is not one of them. That's an odd operation. But all of the even operations make up the icosahedral, or isomorphic the icosahedral rotation group. And this particular state is showing up here with a dimension of 6. So that would normally be a really hard problem. Yamanouchi has made it a trivial problem to at least get the transpositions. Then, once you have this, then you multiply it with the lower bicycles that are, this is 4, 5, then you go look for 3, 4 and multiply it by that and you start getting all of the other elements. And that's something that's easily programmable, so as we go to higher groups, we shouldn't be afraid since we have that wonderful silicon to do it. Now, here, I'm going to note the Pauli exclusion principle at some point, so I want to make a particular thing, but mainly I want to do the S3 symmetry analysis, applying S3 projection. I need to apply S3 projection to those 6 matrices of 1s and 0s, mostly 0s, that are present here for permutation, unicycle, tricycle, inverse tricycle, and then the 3 bicycles. If you can't read it because it's too small, and that's the problem with small boxes, they're going to be small numbers. The bicycle 2-3, 1-3, and 1-2 are in that order that we've been talking about for the S3 and D3 groups. So this comes pretty much straight out of what we've already written down for the irreducible representations. The A1, all ones, the A2, a -1 for the odd elements, a +1 for the even ones, and then finally, this weird tableau that's bent, it's both symmetric and anti-symmetric in some sense, and that's an important thing to discuss, but later. Right now, we just take the matrices that we already have, which consist of minus sign, plus sign of 120 degrees, and then cosine of 120 degrees on the diagonal, and then the inverse of that. And then the rest of them are reflections that are occurring, well, one of them is occurring right in the plane. That's the what we call I3 before, or sigma 3 on the diagram there. That one is already diagonal, and so we've picked a subgroup chain that consists of S2, but just the S2 associated with 1-2 permutation. All the rest of them involve 3 in their notation for their permutations. Only this one lacks the higher group designation of 3. So what we need, and this is, of course, we've discussed in, make a note, I do need to put a link to some of this stuff, because I'm just not used yet to doing it for everything. But the link for the Weil expansion of the irreducible representations, which these are, times the operations, of which we have 6, starting with 3 bicycle, or ending with 3 bicycles, and 2 tricycles, and then the unit operator. So, for the A1 representation, that's the boxes all horizontally aligned, totally symmetric. Every one of the D's is the same 1, 1, 1, 1, 1, 1, 1, 6 times. And what we have to do then is add up every one of these matrices. And that isn't so easy, is it? And it's going to get worse, right? So how do you handle this? This is something difficult and tedious to some, very much, okay? Now here's one way to do it. I mean, normally what I would have done in the old days is I would have gotten some very good tracing paper, and I would have drawn these boxes all on tracing paper and then laid them on top of each other. That wouldn't work so well because tracing paper isn't great. But what we can do is we can math type overlays. That's what works on this, okay? So we're going to do that fairly shortly here. So let's get it set up so we can compare the result that we actually get with the thing that this will give us. Okay, so here we are trying to get that result. How do you do that? Okay, how do you make this thing easy? And particularly, how do you make it for all of the sums that you're going to get where the numbers are different? Okay, what's the most convenient way to do that that doesn't result in you tearing your hair out? And here's what I came up with. You simply take these matrices, math type lets you erase the lines, you just keep the ones and lay it down right on top of there. I just put it right on top of there. For every one of these, okay? So I know the answer here is 1 plus 1 plus 1 is 6. I know the answer here is 2. In fact, every one of the boxes that isn't 0 is a 2. And that's when I discovered something I'd written before had a mistake. For some reason I had left this 2 out. Now that's what I should have gotten, but I didn't. It's right next to the diagonal, I should have seen it. But this is 1 plus 1, everything's 1 plus 1. And you can tell by their positions which one of these matrices it came from, and that means when the numbers are all different, you just take one list of different numbers and just lay it over the top of it and add it up. Okay? So this is really powerful. I think, you know, when we do, there are a lot of problems where you need something like this, and math type will let you do it.
So that was inside math type and not using a canvas or?
No, this is strictly with math type. Even in its terrible state that it is right now, having been sold to Barcelona. Okay? All kinds of things are wrong with it right now. But one of the things it has is the ability to erase the lines.
Or port of attack.
Okay? And it puts things down in a box fashion if you want. Okay? So, you know, that's what I came up with, and that's the way I avoided some mistakes. And I still have a few pieces of hair left too. So I'll do this. Okay? You guys don't have to worry, but just wait. Okay, so the next step is to use that technique with some numbers. 2 minus 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 2. Okay? And this comes out. Okay? Or, even easier, 0 minus plus minus 0 plus. You have to be careful because of the order we have working. That's a very special element, one too, that used to be sitting up in the position that it now occupies. Okay, well, let's apply the projection. What I do want to point out, as I said, we did in this particular thing here, this thing, we took care of the symmetric, and then we took care of the partially anti-symmetric, but we didn't take care of the totally anti-symmetric. And there's a good reason for that. That is the beginning of the basis of the Pauli exclusion principle. Okay, we ignored these because they were all 0. This is non-existent. Okay.
Okay.
They're anti-symmetric, totally anti-symmetric, can't have any two the same. And I only have 2, so if I'm forced to fill 3 boxes with 3 different things and I only have 2, I'm dead. And that's what this state is. It's dead. It does not exist. It takes at least 3 distinct. It takes U3. When we go on to U3, we're going to get to use this thing. But it takes a U3 state to make a 3rd ring, and it will be a determinant on the first go-around. Okay, that's a determinant of coefficients, whatever they are, A, B, and C. Okay, but right now it's 0, all of them, all 4 of them. There's the 4 if we're talking about spin a half, and U2 has its soul in spin up and spin down. So this is a symmetry basis for Pauli exclusion, which we'll develop more fully in later lectures. Okay, so now we've got this, and this, and we have to pull off the kets to make a T that's going to go on which side? Right side. You're right. Okay, but we got to make him first, and each time I have to normalize. Okay, and that's pretty easy because they're all the same number, so it just comes out to 1 over the square root of 3 if there's 3 of them. Okay. Now this one over here is kind of weird because when I go on down, I got a 1 and a 2. Okay. Well, that's a different normalization. That's square root of 6. Okay. But it's the same 1 minus 2, 1. Then this is linearly dependent on something I've already had. So is this. So pretty much don't have anything to add to this beyond what I've gotten here. This is my first thing. That's very clearly linearly independent of everything. This guy right here, well, he's got this and this is linear dependent, so I'm going to scratch them from ever considering them. But this one counts. You can see he's orthogonal to that, so I stick him in here. All right. And then all the rest of them, we have seen them already, so they're screwed out. And then this guy definitely orthogonal to everybody, so that's the last one. Okay, that takes care of the symmetric. Then there's the parasymmetric. That's probably a good terminology for this. And this is a projector that has 1, 1 and 2, 1. That would be for local symmetry coming up. And it also has 1, 2 and 2, 2. That's another pair, and that's what we're getting. We're getting both of those effectively in these columns. So this is the first time the intertwining is really non-trivial. And we're going to, spend the rest of the time here, which will be short today. We're getting out early today. Start late, get out early. Isn't that nice? Okay. So it's about to happen, but let's just do a couple more things here to see what it is that happened, and then we got to come back in the next lecture and codify this. So this is the S matrix that actually arises from doing the thing in the 1, 1, 1, 2 order and then 2, 1, 2, 2. The permutations are going to be reduced, and then the symmetric one is just going to be diagonalized. But whatever was due symmetric, there just came out a whole bunch of representations designated by 3 horizontal boxes. Then the bent box, the one that's partially symmetric, partially anti-symmetric tableau, is taking care of both of these, and these are identical, these 2 matrices right here. Okay? Now, when it comes time to look at how this thing reduces, I have not had time to go ahead and build this, but this is the way you would be making the irreducible representation of dimension 4 for U2. And you know what that is as far as angular momentum theory goes. The dimension 4 representation was spin 3 halves. So this is going to become the spin 3 halves irreducible representation. Completely devoid of raising and lowering operators that come with U2. Now, you could argue, is it easier to use the raising and lowering operators than Clefford-Gordon's and all that kind of stuff, as messy as it is, or is it nice to take your cues from S3? You see, S3 is giving us all of this stuff. So that's a question that you have to answer as we go along. But when you look at what it did for the unitary thing to the last 4 states, you get a kind of a weird thing where you have a unit matrix here, another unit matrix with D12. I'll have to read these to you because the numbers are small. This is D11 right here. And, I see that I've made a typographical error, but you wouldn't have noticed it because you're 10 feet away. That's D11, and that's D11. This is D12, and that's D12. And then there's 2-1 there and there. And finally 2-2 is there and there. So this is kind of a weird arrangement. We've seen this before when we talked about the Mach-Mach principle for the 2-dimensional representations of D3 inside and out, right? We had exactly this situation. One of them was already reduced, that was maybe the inside, and then there was the outside that was all splayed out. And because these are unit matrices, this commutes with that. This submatrix here commutes with that submatrix, just like we were talking about in the simpler case with the triplet singlet, right? So, what you have to do to get this squared away is, if you recall, switch the middle column here. Switch 6 and 7. Now, what is that doing for you? It's doing this. It's turning this one so it now is unitary representations that are sitting blockwise, 2 of them, on the diagonal, whereas over here the permutation relations have been splayed. So this is the T267 flip of its columns and rows, and then you get this. Okay, doesn't affect this, so this stays the same, but this is non-trivial. This bottom thing is non-trivial. So what this is going to turn into is something rather remarkable. Is the frequency of something on this side is going to give the dimension of something on this side, and vice versa. The dimension of something is going to give the frequency of for the other one. That's a super, what we call the reciprocity theorem. Okay, well, we'll get to it. That's for next lecture. okay? We have to go on and take 3 particles with U3 to really see the first non-trivial example of that. And that will give us the 8-fold weight and all that kind of stuff high energy physics so loves. But this kind of sets it up right here. So that's really important. Here we have 2 by 2 D symmetric antisymmetric tableau. Okay, sitting right in where they should be. Here we have them splayed. Okay, now we go with a 6-7 transformation, and these guys get splayed. Nothing happens to these. We have 4 1-by-1 symmetric permutation irreps. That means we have 1 1 1 1 1 1 1 for the transposition P 1 2 right there, and then well, we've already said what that one has. Do it over here, and now you have 2 by 2 D partially symmetric, partially antisymmetric unitary representations. Okay? Now, this one right here, fully filling every box it's got for most of the unitary transformations, of which there's, as I said, octally infinite number of them. This thing right here is a D3 halves irreducible representation. So that's kind of magical that this permutation group, this little S3, which is, you know, formidable at first, but now we're sort of getting used to it, is able to tackle this monster and show you actually what those components are. We just haven't written that all out here. Okay, I think that's about it. I do want to point out where this connects, and I'm going to go ahead with this one too, to the end here where these guys are showing there. Okay, so I want to make it clear that when we did this the old-fashioned way of taking spin a half with spin a half, and that gave us a singlet plus a triplet. That's our 2-particle thing. Then we went to 3 particles, right? And bing, bing, bang, 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 I end up here finally, after a couple of steps, with 2 1/2s and 1 3/2s, right? Well, that's what we got. That's what we've got over there. We got 2 spin a halves in the lower right-hand corner of that matrix, and then 1 spin 3/2 taking up half of the matrix in the upper left. That's the unitary story. That's what angular momentum gives us. So what I've written in this triangle here is the dimension of the tableau associated with permutations, which in this case is the E matrix for D3, or the symmetric antisymmetric combination matrix as dimension 2, with these 2 tableaus designating the base states. And this is all for n equals 3 particles. Here's the other possibility, and this one has 4 states, but there's only 1 multiplet, that is 1 spin 3/2 collection. And so what happens is I add these 4 states plus 2 of the doublets, that's 4 more, is 8, and that's the 2 to the 3rd power that we've been working with here, because that's how many indice combinations I could get with spin up and spin down displayed as a 3rd rank tensor. Now, what we're going to have to do, of course, is go ahead with this and make sure that we can handle what's going on, all of these. But from here on out, there's nothing really new. All we have to do is use the tableaus to give us both the dimension of the unitary group that goes with this intertwining business and the symmetric group, and multiply those 2 numbers together and add all of those products up. That's what's going on in the upper right-hand corner here, and we should get 2 to the nth. So if it's just spin a half, this formula will work. If we're going to go U3, well, that's a whole nother thing that won't be 2-dimensional. This would be tableaus that build up outside, and that's pretty hard to visualize. This is the last one. here, U2, a combination spin a half, that's easily visualizable, unless we can come up with some other way to do it. Okay, well, that's it for today. There's some blank pages that I'll leave in the lecture that you might want to use. But as I say, do it with math type. That's one of many, not many. There aren't many programs that do what math type does.
Not another actor,
But if it does do a matrix, it really helps to take advantage of it, because our new paper is silicon, right? So, any questions? We'll
Yeah, Dr. Hunter, next Monday, I have to attend my friend's defense at noon. Next Monday, not this week.
Right.
So if it's
That's
fine
the
with
day.
everyone, can we start at 10:30 instead of 11? Like, can we have the class on 10:30, 12 if it suits everyone's schedule?
Is that,
Is that okay for
Okay.
you? Next Monday, are you free at 10:30?
10:30 to 1.
12:30 to 12?
Yeah, sure.
What about you guys? Is it fine for you?
It doesn't.
10:30 and
To
12?
12, yeah. Because his
Next
defense is
Monday.
next Monday.
Do me a
Yeah,
favor
that
and send
works.
an email out to the class.
Yeah.
Dr. Harter?
Consider it signed
Can
off
you-
on,
Yeah,
but
yeah.
this will be the,
Yeah.
just for me.
I don't know about Brad or Al.
Yeah.
Al is not registered, so
But he's
Brad is.
attended one.
I cannot come next Wednesday.
next Wednesday.
Yeah, I have to go to Houston for,
Okay.
for visa.
We'll plan on doing a Friday then.
That's fine.
Friday I cannot go back because I have to drive
Oh dear,
Wednesday and back on Friday, you know.
oh dear.
Sorry. But because I can only, they only work on the work day, they don't work on Wednesday. I have to get a visa for German.
Yeah, the office has to be open.
Yeah.
Yeah.
They'll jump through their hoops.
Tuesday, are you free on Tuesday, are you free?
Tuesday is okay.
Luke, you have classes Tuesday?
Yes, I have classes on Tuesday.
On Tuesday. Yeah, well, I still got that graph that looks like this with all the spots filled except for here, here, and here. And so it is really hard to make a move. But
What about have
It is.
an extra class this Friday? If
that's the one that's still open.
no, if that's
If
fine.
we go at 2 o'clock, 3:30. Yeah, if we go at
You're
2
not back
o'clock
on Friday.
on Friday, everybody supposedly
I'll
could.
try.
Okay,
What's
she
this
might be
Friday?
able to make it back.
This Friday I'm okay, but next Friday.
No.
The following Friday.
Oh no, what I'm saying is we can have next week, one of the classes of next week this Friday, if that's fine with everybody.
I'm good.
Yeah,
I'm good.
Yeah.
Well, there's a little bit of a problem because at this point I am creating new material.
Oh, okay. Oh, you do it on the
and
weekend.
This means I don't get any sleep
Okay.
if I, put it too close together.
Well, I mean,
You see,
I can, if
Vouch for that.
yeah, that's so. I'm the one that's going to be.
We keep post about.
I could come in and give you what I
12:40
got
last
would
night.
be
He was
2
working
slides
till
and we
after
leave.
midnight last night.
Oh,
I just
well, I
backed
hope
you up
this
a
Friday there is not like a time confusion for me because I'm planning to read this and ask you questions about it.
If
Okay,
you have
that's fair
3
game.
classes, the next week after following week, I'll be okay.
Yeah.
Then we can start piling them
Yeah.
on.
That's
Because
fine.
we have a makeup anyway.
Well, we can always just say, okay, we'll put it off and see if we can get it done during dead week or something like
that's
that.
perfectly fine. too.
Because we do have at least 28, maybe 29. I'm trying for lectures, but at this point, I can compress and make that number smaller. We'll see. We'll figure out. Yeah.
Having a little space in between those
Yeah.
classes. will
I mean, that's the advantage
Both
of
sides.
having a video that goes on the web. As if you do miss a class, it's, you're not, you don't miss it.
Yeah.
You can go get it. But I prefer to, of course, have it
So it's a bit
done human to human rather than have the silicon in between us. It's so, it's been encroaching lately.
So
Yeah. Okay.
yeah,